Problem 5.170 or 6.165 for the given textbooks. For details, please see the description below. An adiabatic air compressor is to be powered by a direct coupled adiabatic steam turbine that is also driving a generator. Steam enters the turbine at 12.5 megapascals and 500 Celsius at a rate of 25 kilograms per second and exits at 10 kilopascals and a quality of 0.92. Air enters the compressor at 98 kilopascals and 295 Kelvin at a rate of 10 kilograms per second and exits at 1 megapascal and 620 Kelvin. We need to determine the net power delivered to the generator by the turbine. We start the problem by writing the mass balance. We see that the mass flow rate going in minus the mass flow rate leaving is equal to the change of the mass in the system. Since this is a steady system, this value is going to be equal to 0. Notice that for each one of the components there is only one entrance and one exit. Therefore, the mass of each component going in is equal to the mass flow rate leaving each one of the components. Now, if we do the same process for the energy, we find that the rate of change of the energy going in minus the rate of change of the energy leaving is equal to the change of the energy in the system. Once again, this is steady. Therefore, the rate of change of energy going in is equal to the rate of energy leaving the system. And now we have to write for each one of the components. Let's just start with the compressor. To be consistent with the notation, we're going to label this as 0.1, this as 0.2, this is 0.3, and this as 0.4. So when we have the compressor, so we're going to start with the compressor. The amount of energy going in is going to be the mass going in at 0.1 times the enthalpy at 0.1 plus the amount of power that is provided from the turbine to run the compressor. That is going to be power going in, and that is going to be equal to the mass leaving, which is going to be mass flow rate 2, 82. Notice that for the compressor, the mass going in and the mass leaving are exactly the same. So, and then we're just gonna write it as m.1 is equal to m.2, and we're gonna write it as the air mass flow rate to be consistent. So the work going in for the compressor is going to be equal to the mass flow rate of air and the difference between the enthalpies of the entrance and the exit of the compressor. We're going to do the same analysis for the turbine, and then we see that the the energy going in is going to be m3, that 3 times the enthalpy at the entrance. The amount of energy leaving is going to be that 4H4 plus the work that is produced, the power that is produced. Once again, the amount of mass flow rate entering and exiting the turbine is the same. So it's going to be m.3, m.4. We're going to write it as m.s for steam. And then what we're looking for in this case is the work leaving the turbine, the power leaving the turbine rather. So this is a steam, and this is H3 minus H4. Now the next step is to find the values of the enthalpy at each one of the stages provided. To find the different values of power for the compressor and the turbine, we need to find the value of the enthalpy. We're going to start by the compressor. Since it's compressor, the driven fluid is going to be air, we're going to go to table A17. In table A17, we go to the initial temperature, which is 295. And then we find that at that temperature, the value of the enthalpy is 295.17 kilojoules per kilogram. The final temperature is 620. And for that, we find that the enthalpy value is going to be 628.07 kilojoules per kilogram. Now that we have the values of enthalpy for air, we are substituting to find the power that is delivered from the turbine into the compressor. So we find that the work into the compressor is equal to the mass flow rate of air, which is 10 kilograms per second, and H2 is 628.07 minus 295.17, and this is kilojoules per kilogram. Kilogram and kilogram cancels. Kilojoules per second is a kilowatt. Therefore, the power driving the compressor is equal to 3,329 kilowatts. Now we're going to find the values of enthalpy for turbine. For turbine, the working fluid is going to be water. Water enters as a steam into the turbine. Therefore, we're going to go to table A6. And the pressure that is given is 12.5 megapascals. And the temperature at that point is going to be equal to 500 Celsius, which tells us that the value of the enthalpy is equal to 3,343.6 kilojoules per kilogram. On the other hand, point 4 provides us a value of quality, which indicates that is a saturated mixture. Therefore, we need to go to table A5. Since pressure is the quantity that is provided, we have 10 kilopascals. And then for that, we find that the value of HF is equal to 191.81, and HFG is 2392.1, both values in kilojoules per kilogram. We're going to use those two values to find the value of the enthalpy at point 4. Once again, to find the value for the enthalpy at point 4, we find the values of HF and HFG, and the quality to be 0.92. We substitute these values, and we find that H4 is equal to 2392.5 kilojoules per kilogram. Now we substitute the values of H4, H3, and the mass flow rate of steam to find the power leaving the turbine. So the mass flow rate of steam is equal to 25 kilograms per second, and H3 is 3343.6 minus 2392.5, and this is in kilojoules per kilogram. And then notice that kilogram and kilogram cancels. Kilojoules per second becomes kilowatts. Therefore, the power leaving the turbine is equal to 23,771 kilowatts. Notice that the amount of power delivered by the turbine is divided into two ways. One to drive the compressor, and the other one to drive the generator. Therefore, the power done by the turbine is equal to the one provided to the compressor, and also the one provided to the generator. Therefore, the difference between the output of the turbine and the one provided to the compressor is what is going to be driving the generator. So we take this value minus this, and we find that the work to run the generator is equal to 20,448 kilowatts.